in our Mech Minutes Timing Belts and Pulleys series. If you're looking to get familiar with the difference between timing, round, V, and flat belts and pulleys, check out our first episode for belt and pulley basics. In this episode, we'll be examining the warning signs that your timing belt is wearing down and might be about to fail. If you've installed and are using your timing belt correctly, there can often be no warning of wear before it fails. In this case, it's highly recommended to replace the belt at the manufacturer's specified lifespan as preventative maintenance to avoid catastrophic failure and machine downtime. Most belts are designed to last 3 years, given 8 to 16 hours operation per day, 5 days a week. Determining whether a belt has wear signs due to improper setup or operation usually does not require special tools or equipment. Most of the following can be identified visually without too much effort. When a belt is installed without proper alignment, one side of the belt will typically show more wear than the other. Key symptoms include cracked teeth or a single frayed edge, and occasionally tooth radius cracks may appear as well. Crimp failures lead to stress concentrations in the belt after it's folded over. Unfortunately, the most common way to detect this issue is upon belt failure. The belt may appear almost to have been cut with an even break across the width of the belt. Ensure your timing belts are stored properly, are not folded over or bent past the specified bend radius, and avoid using improper tools like screwdrivers to remove the belts. An over-tensioned belt or extreme temperature can cause excessive wear in the valley or land area of a belt. In this case, the tensile cord within the timing belt will be exposed between the teeth. To avoid this, make sure your belt is tensioned appropriately and not exposed to temperatures exceeding the manufacturer's specifications. Other environmental factors, including contaminants like metal, dust, and other abrasives, as well as chemical exposure, can lead to excessive wear or cracks. This can be easily seen as uneven cracks across the back of the belt. And finally, a belt which is tensioned too loosely can exhibit fit failure by shark toothing, where one side of the belt's teeth is more worn than the other side, creating a shark tooth appearance. The next time you're concerned that your timing belt might be about to break, check for any wear signs to determine the best way to keep it running smoothly. This can help prevent machine downtime and maximize belt lifespan. If alignment questions have you worried, tune in to the next episode to learn more and alleviate your concerns. In the previous episodes of Mech Minutes, Timing Belts and Pulleys, we looked at belt wear signs and some common causes of excessive wear and failure. In this episode, we'll take a closer look at one of those causes commonly encountered during setup, belt and pulley alignment. Proper alignment is an essential component of maximizing your timing belt's full potential. Misalignment, at best, can lead to premature wear or frayed edges, climbing the pulley flange, and in worst cases, reduced load transmission, system efficiency losses, running off the pulley completely, and early belt failure through unzipping. Misalignment is the biggest reason that belts fail, with improper tensioning following close behind. There are two main types of belt and pulley misalignment: angular and parallel. Determining whether misalignment is present in your system is a relatively easy and straightforward process, and only a straight line, commonly a straight edge or a laser, is required. Start by choosing 2 pulleys in your system to compare at a time, and place one end of the line across the diameter of one of the pulleys. Extend the line towards the other pulley and take note of how many points of contact the line has with the second pulley. If the line has full contact, 4 contact points laying plumb, with both of the pulleys, your alignment is correct. If, however, the second pulley has only 1 point of contact, there is angular misalignment in your system, and you need to make adjustments to the angle at which the pulleys are mounted. If there are no points of contact between the line and the second pulley, or if the line overlaps the body of the second pulley, there is parallel misalignment, and the position of the second pulley needs to be adjusted along its axis. Occasionally, your system may have a combination of parallel and angular misalignment, and in order to correct the alignment, you will need to alternate between measurements and adjustments. Once you've identified and fixed any misalignment between the first two pulleys in your system, you can repeat the process using one of the correctly aligned pulleys and any other in your multi-pulley system until all issues have been addressed. Now that you know how to properly align your timing belt and pulleys, the next step to ensuring your system setup is belt tensioning. We'll take a look at how to achieve optimal belt tension in the next episode of Mech Minutes, Timing Belts and Pulleys. Welcome to the next installment in our Mech Minutes Timing Belts and Pulleys series. This episode will continue discussing essential installment and setup steps, focusing specifically on belt tensioning. Watch the previous video for keys to successful alignment and episode 2 for more on how to diagnose symptoms of belt wear. If all this sounds new to you, we recommend checking out the first episode for an introduction to the basics of belt and pulley systems. There are two main methods for adjusting belt tensioning in a system, using the plunger method and using the sonic tension meter. To adjust tension using the plunger method, you'll need a spring tension tool. This consists of a shaft and plunger with a deflection distance scale, deflection force scale, and an O-ring for reference. Start by finding the appropriate force and deflection for your belt from the manufacturer's specs. Then, using a straight edge against your belt as a point of reference, position the O-ring on the deflection scale to determine how far you need to move the belt. Once this is done and you've pressed the tool into the belt to the correct deflection, read the resulting deflection force on the shaft and adjust the belt tension accordingly. A sonic tension meter doesn't use deflection to determine tension. Using a principle common to any guitar player, it measures the sonic frequency of a plucked belt to calculate the belt tension. Usually you will need to input the length of your belt into the sonic tension meter in order to be correctly calibrated. Then, after plucking the belt to begin oscillation, hold the microphone over the belt in order to capture a reading of the sonic frequency. Each sonic tension device may have slightly different procedures. Consult the manufacturer of yours to appropriately utilize it. Once you've taken the measurement of the tension, adjust the belt to land within the manufacturer's specifications. Now that you've selected the appropriate belt and pulley for your application, gotten your pulleys aligned, and your belt properly tensioned, you're nearly ready